Hello, welcome to today's presentation on visualization. My name is Brett Champion, and I'm the manager for the visualization team here at Wolfram Research. And we're going to be looking at some newer features in the Wolfram language with regard to visualization. And in particular, we're going to start with talking about scaling functions. And the scaling functions have been around in the system for a while, and we've recently been improving and expanding on them. And then we're going to look at a new visualization function called Ternary list plot. And then time allowing, we'll look a little bit at using the new drop shadowing style in visualization functions. So typically for visualizations, the most common scale is just a normal linear scale. And after that, probably the next most common one is a log scale. And log scales show orders of magnitude as the same visual distance. So 1 to 10, 10 to 100, 100 to 1,000, etc., all take up the same amount of space on a log scale. And we can see that in this plot on the left, where we actually have in the y direction a log scale that is being labeled in 2 orders of magnitude at a time. So factors of 100 from 1 to 100 to 10,000 to a million. And on the right-hand plot, we have a log scale along the x-axis, and it's going both above and below 1. So we're getting 10 and 100, and then 1/10 and 1/100th, etc. And log scales are so important in various fields and in science that since version 6, we've had built-in system symbols in the Wolfram language just for doing plots with log scales. So we have log plot and log linear plot, and those are the two that you see here. And then log plot, which has a log axis on both of them, and list versions of them, and date list versions of them. And if we wanted to expand out, then that's a lot of functions that we have to add. And so what we did instead is we added an option to the visualization functions called scaling functions. And as I was saying, there's 2 reasons for adding the scaling functions option. The first is to avoid having to have log versions of everything. So for like plot 3D, you would potentially end up with a log linear log plot 3D, and a log plot 3D, and a linear log plot 3D, and all the different combinatorial ways of specifying whether you want each of the 3 axes in a plot 3D to be log or linear scaled. And the second reason is to allow more scaling functions, more ways of doing scales than just linear and log. And so here we have 2 of the other built-in scaling functions: reverse, which just runs the axis backwards. So instead of increasing going from left to right or bottom to top, it increases going from top to bottom or right to left. So here we have a reversed y-axis on this plot, and you see 0 at the top, 10 at the bottom. And the other one is reciprocal, which basically does what it sounds like. So instead of plotting, so it places 1 at 1 and 2 at 1/2 and 3 at 1/3 and so on. And so it expands out things a little bit around 1 and compresses things that are farther away from 1. And so for several versions, these have been sort of the main built-in scaling functions that we've had: log scales, reverse, and reciprocal. And it's useful to think of, there's sort of how scaling functions work. And there's 2 things that a scaling function does. One is that it does the actual transformation of the plot. And so here I have on the left plot of an expression with scaling functions goes to log, And on the right, I'm plotting log of the function instead. And the curves look exactly the same in terms of where the blue line is relative to the box around it. And that's the first part of what scaling functions does, is the actual transformation of the geometry of the primitives, of the curves and lines and points and whatever. The second part of what scaling functions does is to then correct for that when we're looking at the axes and the ticks and that sort of thing, so that we still have meaningful numbers that reflect back on the original plot along the axis so that it's easy to read. So 4 squared is 16, and some minor term for sine of x. And so if we trace up from 4, we're up here at a little bit above 10, and so this is 10, this is 20, so it's quite reasonable that this is a value of 16. Whereas if we look at where we just manually applied log, we'd have to sort of mentally think of, okay, what is e to the 2 point something, and it's not nearly as nice to get back to whatever the actual that 16 value. And so those are the two parts of scaling functions: the transformation going one direction, and then correcting for it, sort of coming back the other direction, so that your coordinates are still in nice things to talk about and to think about. And so the scaling functions we looked at so far, log, reverse, reciprocal, these are all implemented using functions that are nice mappings from real numbers to real numbers, or relatively nice mappings from real numbers to real numbers. So log is transforming by just applying log to things, reverse is negating it, and reciprocal is taking the reciprocal. And then those have sort of inverse mappings that get used to account for the labeling. And so for log, it's going to be x, and then conveniently for reverse and reciprocal, it's just the same function again. So negation and reciprocality are their own inverses, and so it's the same function doing both bits of work. And so scaling functions, I think, was originally introduced in version 7 thereabouts, and we've been rolling it out in pieces to more and more functions. And at this point, we have about 80% of the visualization functions support scaling functions. And so most recently, a lot of the vector plotting functions have picked up support for scaling functions, and some of the parametric type plots, spherical, revolution plot 3D, that sort of thing. And so that's been one sort of big block of effort that doesn't necessarily isn't fancy in itself, but if you need it for one of these visualization functions, then it's there as a tool that you can use. And the other thing that we've been doing to expand scaling functions is adding more built-in types of scaling functions. And so we've added a signed log scaling function, which is similar to log, except does a little bit of work so that we can deal with negative numbers and even 0. And so it has to shift a traditional log scale a little bit to be able to show those. And then we've also added infinite scaling functions. And so these are actually used by default if you do a plot with infinite bounds on the variable. So plot of x goes from -infinity to infinity. And in this case, the curve doesn't get all the way out because the automatic plot range calculation clips it at plus or minus 40-ish. But you can see that the x scale includes minus infinity, and it includes infinity, and it's sort of there's a lot of range in here between minus 10 and minus infinity, or between 10 and infinity compared to 0 to 10, say. And there's some ways of controlling sort of how much of a more linear scale you see in the middle here, and how much is pushed out to the edges. And like I said, this is done automatically if you have these variables, if you have these limits as infinite values, or you can specify it explicitly. And so in this case, I'm doing the same plot, except I'm saying that I also want the I also want the y-axis to be an infinite scale. And so then we have infinities on the y-axis, and this, our line has straightened back out into a line, and the nonlinear transforms have sort of canceled each other out in this case. And it's sort of an interesting question of, if you have an infinite domain, do you want an infinite range as well? And there's cases where you do, and there's cases where you don't. And so, since we haven't figured out a good way of determining when you want which case, at the moment you have to manually specify if you want that range to be an infinite scale as well. And so these are two of the more recent built-in scaling functions. They're still pretty much real number to real number type scales. Nothing too exotic there. So getting into the more exotic case, we are allowing dates to be used as scaling functions, to have date-based scaling functions. And so in the past, again, since version 6, we've had date list plot, and I think date list log plot probably got introduced in about version 7. But wanting to add support for dates, for data with dates in it, again, we don't want date list plot 3D and date contour plot or whatever. And so scaling functions is sort of the best place to add that parameterization and allow that type of functionality. And so I'm going to show an example, and this is one of my favorite examples to recreate every few versions and see if we've made it simpler to do over time. And so this is plotting sunrise and sunset for Champaign, Illinois, where our company is headquartered and where I live, and plotting sunrise, sunset over the course of the year. And so I'm creating my data, and so it looks like a date and a time when the sunrise is, and I'm wrapping in a time object to throw away the normally sunrise would return this time on that date, and that doesn't plot quite so well. And so I'm throwing away the date part of it and just reducing it to 8:15 a.m. And so I have a year's worth of things like that. I have the same for my sunsets. And then I say list line plot of my rise and sets. And I'm setting my scaling functions to date on the x-axis and date on the y-axis. And so now I can see sort of where the days are short and where they're long, and sort of the interesting asymmetries and things. And admittedly, at the moment, this version isn't accounting for daylight saving time. It would be a little bit more work to correct for that in the construction here, and I wanted to keep it a little bit simpler. And even though this is time object instead of date object on the y-axis, it's still a date scale, and that's still the scaling function we're going to use for that. And so then we started getting into really interesting uses of scaling function, which is, what if we don't really restrict ourselves to um, um, continuous types of data and inputs. And so then we tackled categorical scales. And we have two types of categorical scales that we've added to the system, nominal scales and ordinal scales. And there's really not a lot of difference between them in many ways. The difference between nominal scale and ordinal scale is nominal scale is just a collection of things. You can't say anything about it. So it might be people's names, it might be locations, it could be models of a car, or companies in a city, or offices in a company, types of fruit, all these different types of things that you might have lying around as a named type of thing. And ordinal scale is very similar. And the difference is that with ordinal scale, you're saying that these are categorical things, but there is an ordering to them of some sort. So it could be things like letter grades in a class, A, B, C, D, E, F. It could be, the magnitude of a tornado, so the EF3 type stuff. It could be credit ratings, or if you go to the doctor and they ask you, what your level of pain is, they typically have like a 10-point scale going from no pain at all to this is the worst that I've ever felt in my entire life. Or star ratings, 1 star, 2 star, 3 star type things might be a categorical scale if you aren't allowing things like 3.5 stars. And so I thought we would, sort of look at a few examples of these to give some ideas to people and encourage their use. And so the first is an example of apple prices, Apple the fruit, not the company. And so we have data here that I don't remember exactly where it came from that we acquired. And we have a nominal scale along the x-axis. So it's, what is the type of apple? Is it a Red Delicious? Is it a Honey Crisp? Is it Granny Smith? What? And this is just a nominal scale. There's no order to it. They're not being displayed alphabetically. They're not being displayed, by average price or anything. It's just, here are 7 different types of apples that you might see at a grocery store. The vertical axis is an ordinal scale. And so these numbers basically represent roughly the size of the apple. So I think this is, there are roughly 56 apples in, I forget what, volume of measurement they use for that. So these are relatively big apples because you don't have a lot of them in the, in the crate. And these are smaller apples because you have more of them. And so that's an ordinal scale. These are going from smaller apples to larger apples. And the difference in how you deal with them is really not that much. The main difference at the moment is that if you have a nominal scale, you can just say this axis, this scaling function is a nominal scale. I'm going to put automatic in the first argument, and it's just going to go through, and anytime it sees something new, it will say, oh, there's Granny Smith. That must be another item in my nominal scale. I'm just going to add it to the list, and create an axis, included on the axes and as part of the scaling function. Whereas the ordinal scale, because there is an order, you have to specify what the categories are, and that is simultaneously specifying what the order is for that ordinal scale. The next example I'm going to look at is similar in that we have a nominal scale on the x-axis again, and it has an ordinal scale on the y-axis. And this is S&P bond ratings for each of the states as of sometime last year. I'm wondering if the data actually got updated earlier this year, so that might be a little bit out of date in the labeling of that iconized data. And so here we have the states, and in this case, they're just listed alphabetically. There's no ordering implied there. And then we can see what the S&P bond rating for credit rating is for each of those states. And we're displaying this as a stylized list plot. And so, I mean, at the moment, nominal scale, ordinal scale, probably you're going to be looking at more the data visualization functions, your list plots, bar charts, bubble charts type of thing, rather than your plots and plot 3Ds. But, there may still be cases where you're plotting a discretely valued function. And so that may come into a nominal scale or something. And so that is the advances we've made and changes we've made to scaling functions in the past year or so, give or take. We're also going to now look at ternary list plot, which is typically used for looking at how of mixtures of things, and particularly mixtures composed of 3 different types of components. And it uses some cleverness to take 3 numbers and display it as a 2D plot, as a 2D point. And the trickery it uses, the cleverness, is that it treats them as percentages. And so and I see we have questions. I want to get to them at the end. And so I want to get through the primary material first. And so the cleverness that it uses is that it basically normalizes everything into percentages, and then you have a relationship that all 3 things add up to, say, 100%, and that allows you to effectively remove a variable. And so then, even though you have a point here, you can read it off to what the constituent fractions are. And the ternary list plots are not as familiar to everybody, and so it can take a little bit more time to get used to interpreting them and figuring out what you're seeing when you look at one of these. And so I have an example, a couple of examples I want to go through that show a couple of things that you can read off from a ternary list plot, from a ternary plot. And so here I have, I'm going to make this a little bit bigger. I thought I had, but so we have a ternary list plot, and by construction, each of these sets of points corresponds to a fixed percentage of the value being A. So if we take this blue set of points, this corresponds to mixtures where 70% of the mixture is A. At this end, 30% of the mixture is B, and 0% of the mixture is component C. And at this end, 30% of the mixture is C and 0 of it is B. And so you sort of have our A scale goes from 0 to 1, and each of these is going to read off along this direction. These points are covering up the grid lines and the corresponding to the A axis. These grid lines that are going, sort of from this top left edge of the triangle down to the right correspond to C, and the horizontal grid lines correspond to the B values. And so if I was to pick this point, then this is 60% B and 20% C and 20% A. And so even though we have three values that we're looking at, because we know that everything adds up to 1, we're still able to read off what the relative components are. We can't necessarily read off what the actual values were because there's no requirement in ternary list plot that all of the points actually add up to the same amount. It could be that one point of 3 numbers adds up to 10, and one of them adds up to 100, and one adds up to 75 or whatever. We're just looking at the distribution within each sample into the relative proportions of A, B, and C. The other thing that we can look at is the ratio of points of components. And so let's reevaluate that real quick. I have an experimental thing turned on. So here, each of these sets of points is showing is a constant ratio of component B to component C. And so like if we take this point here, this is about 35% C, and it is about 70%-ish of B and 0A. And so that should be, I think in my green, which didn't get magnified, is my 2-to-1 ratio. If I come down here to like 0.2 there, I'm at 0.55 and about 0.25 if we trace back up to that point from there. And so everything along here is sort of at a 2-to-1 ratio of B to C. And unfortunately, the ticks don't reflect that in an easy way quite so much, but if you have lines going into one of the vertices, then that is a fixed ratio. And so next we'll look at some examples of this, and it was really sort of interesting because, I mean, traditionally, I mean, the oldest versions of this type of plot that I know of were basically color mixing. More recently, it's come up a lot in geology and looking at soil texture and soil composition of sand, clay, and silt. To the point that the US GS has sort of named categories for different regions in this triangle, which we've recreated here. And so, and the way that we've created it is a point that I wanted to point out, is that I have a polygon, so like this orange polygon in the middle here. I'm giving the relative the triples that correspond to each of these corners, and then it is automatically transforming that polygon from a polygon that looks like it should be a 3D thing to a thing that will display in 2D in this, and then so on for all the other polygons. They're just iconized away to because they're not that interesting. So other things that you might look at are, what are the in terms of nutrition, what is the fraction of a food or a diet that comes from, where your calories come from fat, carbohydrates, or proteins. And so here we have a bunch of foods from Wolfram Alpha, for which we're looking at their components. And so down here we have everything that is so this is going along the fat scale, and let's see. So obviously this has protein. These are all the 0 carb things, right? So 0 carbs is here, the horizontal line. All this axis is 0 carbs. And so we have basically different types of meat sprinkled throughout. And then, a seasoning here that I think probably is 0 all the way around for everything. And so it's sort of an outlier. But so for dieting purposes, you might be looking at these sorts of things. And then I forgot to change the style on that. But the other one is that I thought was an interesting thing to look at was where different countries get their electricity from, what the source is. Is it coming from renewable green energy? Is it coming from nuclear? Or is it coming from fossil fuels? And so the bottom axis here is basically all the countries that have none of their energy coming from nuclear. And then we have, say, France up here, which has almost 80% of their power coming from nuclear energy. And then, countries that Sweden and Switzerland that have a lot of their energy coming from renewable sources, including Zambia, which I can't get the tooltip to come up. There we go. Which is almost entirely renewables. And in that case, it's hydropower that they're using for their electricity in that country. And so the last thing I want to look at briefly is drop shadowing, which was a new 2D style directive that was added in 13.1, which draws a primitive with a drop shadow underneath it. And this is a style that can be used anywhere that styles can normally be used in 2D graphics, whether it's plot style to style these curves so that they have a little shadow and look like they lift off the page a little bit, or say in a pie chart, where we get a little shadow under each of the sectors. And I've popped this one out because of there's one of these sectors always has to draw on top, and it's going to draw its drop shadow on top of everything else. And so I popped it out to hide that fact, sort of. And so I think it'll be interesting, to see what people do with drop shadowing and how they use it in plots and graphics and whatnot. And so now I'm going to switch over to see what we have question-wise. Let's see. So for the scaling of infinite scales, so this slide. All right, so how is the infinite scaling done? So it is, obviously plot is still sampling at a finite set of points. I don't remember. I mean, there's a lot of different ways that you can do an infinite type scale. And so Sander was, wondering whether it was arctan, and I think it's not. I think it's actually we have the ability to do it with arctan, and you could write your own scaling function that did it with arctan as well. But I think it's actually using whatever, it's somewhat arbitrary. It's a rational-ish function that actually, that we're actually using, but depending on what function you use, it sort of affects, how fast the transitions are, in terms of, this middle section and how steep these curves are. And so we picked one that we thought looked, sort of nice, that it wasn't too sharp of a corner going through the S shape. Let's see. Right. So I think this question got asked in an earlier session. And it's how to do large plots with lots of points faster. So like 10 million points. And the best way is to not do plots with 10 million points. And let me see if I drop to the end. Let's get some space here. It took a little bit of time. I'm not sure why. I wonder if I had a enter key stuck or something. Or actually it was just how I was entering things. And so this takes, actually, I'm going to create a new notebook, and then I don't have to deal with the presentation notebook doing weird things sometimes. $10,000, let's do 100,000. Okay, so that took a little bit of time. I'm just going to do it again just to make sure that we didn't have any initialization stuff happening. So for a plot like this, you don't really need all 100,000 points. And so if we include max plot points and we drop this down to like 100, then we get a a curve that looks pretty much the same at a much faster speed. And so, I mean, in general, the viz functions, if you give them 10 million points, they're going to process the 10 million points. And some of the stuff, I'm sure there are places where we can improve speed with large data sets, and it's something we look into periodically. But the best approach really is to try to avoid using 10 million data points for things. And because if you do a list plot with 10 million points, we're going to generate a graphic with 10 million points. The front end is going to render it with 10 million points, because we don't know that, all the points aren't necessary, or that they don't all, end up looking smooth. And so it doesn't know where to throw away points. And so it, sort of has to deal with all of them. Right. I mean, and as somebody else is commenting, 10 million points is silly because there's not 10 million points here. I mean, even, I guess you get into, you're getting close to 10 million points with some displays these days, but your entire chart isn't, your entire plot isn't going to use it. And so you can use max plot points or other techniques to trim things down. That will help. And let's see. There's several questions about, or comments about, user interface that I'm not going to get into because it's not my area. And I'm not the best person to speak about that. But when are we going to modernize charts? Look like they're from 2005. It's coming up. I think we're collecting ideas on things that we want to improve stylistically on a lot of the visualization functions. It hasn't quite hit a critical mass of ideas and concepts and improvements we want to make a big jump on things, but there are definitely things stylistically, and there's things functionality wise for all the different plots and charts that are coming up, and I can't really speak about them in any specificity right now. But if you have specific comments on ways that you think things could be improved, we're happy to hear them. A lot of times there's a little thing here and a little thing there, and you build it up, and then you have something that looks significantly different just by an accumulation of small changes. And so we're about at the end of our time. And so let's see. Okay, one last comment. Somebody is commenting something that's broken, which I don't recognize it immediately. So dateless plot range goes from that to that. Oh, that's cute. I don't recognize that one, so I don't know what's going on there, why we aren't getting values on the left here off the top of my head. So we'll look at that. Date ticks are, I think, an area that, one of those areas that's rich for development and modernization, but that's just a straight up bug. So thanks for drawing my attention to it. And thank you everybody for joining me today, and we will have more of these talks get scheduled for next month. I don't remember if we actually, I guess next week is next month, but I don't know what the schedule is. I'm sure it will be posted on community soon. So thank you for attending, and we'll stop here.